नमस्कार, सुस्वागतम, अभिनंदन, केम छो, आदाबर्स, वणकम, सत श्री अकाल, अंबागड़ी, राधे राधे, एंड वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का 105वें पीआरएल के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। आई, Anil Bharadwaj, very warmly welcome you all for the 105th PRL का अमृत व्याख्यान। We started the PRL Kamrit Vyakhyaan as a part of celebration of PRL's 75 years of establishment, which coincided with the Azadi Kamrit Mahotsav, which celebrated the 75 years of independence of India. And also, it is to celebrate the rich history and legacy of the contribution of PRL in the area of physics and space sciences. This is also to pay tribute to Dr. Vikram Sarabhai, the founder of PRL and the father of Indian space program. So we started this on 4th of August 2021 with the sankalp that every Wednesday at 4 p.m. we will have the PRL Kamrit Vyakhyaan. We completed uninterrupted 75 episodes of weekly PRL Kamrit Vyakhyaan in January 2023. And subsequent to that, we are hosting now monthly Vyakhyans. So today we have the 105th PRL Kamrit Vyakhyaan, and we have yet another very distinguished Vyakhyaan Karta with us, Professor G. Baskaran, who is a distinguished professor at IIT Madras, emeritus professor of Med Science in Chennai, as well as visiting professor at Parameter Institute of Theoretical Physics, Waterloo in Canada. And he is going to speak to us on quantum origin of modern artificial intelligence, which is also a very pertinent topic in current days because AI is being talked about at every place. So we thank Professor Baskaran for agreeing to our invitation and to be with us today at the 105th PRL Kamrit Vyakhyaan. I now request my colleague Professor Navinder Singh to kindly introduce today's Vyakhyaan Karta to the audience on the WebEx, as well as those who have joined us live on PRL's YouTube channel. Over to you, Navinder.
Yeah, thank you, Professor Bharadwaj. It's really a pleasure and honor to introduce today's Vyakhyaan speaker, Professor Ganapati Baskaran. So Professor Baskaran is a world-renowned theoretical physicist with a broad interest in quantum matters, also explores prospects for room temperature superconductivity, novel quantum phases, qubits at ambient conditions, nature, biology, and neuroscience to continue amazing. Professor Baskaran completed his school education in Tamil medium at St. Mary High School, pre-university BSc Physics at Tyagaraja College, and MSc Physics at the American College, all at Madurai. He completed a PhD in theoretical physics at the Indian Institute of Science, Bangalore. I am honored to share one connection with Professor Baskaran. My PhD professor, Professor N. Kumar, Professor Narendra Kumar, ex-director of Raman Research Institute, Bangalore, also mentored him during his PhD days in IISc in 1970s. From there, Professor Baskaran went to ICTP and then to Princeton to work with the Nobel laureate, Professor P.W. Anderson. With Professor Anderson, he developed what is now known as the resonant valence bond theory of high temperature superconductors, which is one of the leading proposals on the mechanism of high temperature superconductivity in cuprates. This has been labeled as one of the most difficult problem in condensed matter physics. So in a paper, P.W. Anderson writes about him. So I have Professor Anderson's paper with me here. This is one of the very famous paper. So Anderson writes about Professor Baskaran in this way. I will briefly read it in a very short paragraph. So I think it was Ted who told me about the structure and what then I then was explaining to Baskaran. So he's speaking, Professor Anderson is speaking about cuprates. I began to see the picture. Baskaran will play a big role in what follows. He had come to me from ICTP in Thursday with the warm recommendation of my old student from Cambridge, Irio Tosati. Baskaran is brilliant and quick off the mark. Perhaps it is a Tamil trait that he speaks loudly and with assurance. Certainly he shares it with others I know, but perhaps a component of unfolding is the fact that his conclusion jumping resonates with my own. Baskaran was to be enormously sportive and helpful, but occasionally he was so whether I was right or wrong. This is Professor Anderson, Nobel laureate, writes about Professor Baskaran. This is very respectable. Okay, so I move forward. So he joined the Institute of Mathematical Sciences, Chennai in 1987, and now a professor emeritus at there. He's a distinguished professor at IIT Madras and distinguished visiting research chair at Perimeter Institute of Theoretical Physics, Waterloo, Canada. He's a fellow of the Indian Academy of Science, Indian National Science Academy, the World Academy of Science, UNESCO. He has received ICTP award for his pioneering work on high temperature superconductors. He has received SS Bhatnagar Award, Distinguished Alumni Award of IISc, GN Ramachandran Award of the Sastra for Theoretical Physics. He also writes popular science in Tamil. Today he is going to speak on quantum origin of modern artificial intelligence. Without further ado, I would like to request him to share his screen and deliver his Amrut Vyakhyaan. Professor Baskaran, please. So you need to share your screen.
So Bhaskaran, I think you have to unmute yourself also.
Yeah.
Bushit, can you unmute him?
I have sent him a request to get unmute.
Acha, he himself has to unmute.
Yeah, he himself has to do that.
Now is it better?
Yeah, we can hear you.
I'm sorry, presentation. Oh, sorry. Skip. Nothing is something happened. Sorry. People are responding. Please pardon me.
Okay, no issues. Just share your slides.
No, I am not able to.
Are you able to see the share in the bottom?
Yes. It's escape is okay. Sir, I'm having some problem with opening my.
Sharing right is given Bushit. I think that is already there, right?
We had tested it in the beginning.
Yeah, just now we tested all just before.
Sharing right should be there.
Yeah, you can send the PDF file of the presentation to email to us, then we will share from our end. If
So shall I do that?
I think if he can exit and rejoin, then that can also.
Yes,
if we
that
reach
will work.
Can
So
come
please
out of this.
rejoin. Log.
Yeah, I'm not able to come out of this rejoin.
that means got
There is
hanged
a
actually.
cross, red cross towards right, in the bottom.
This is
Yeah.
a red button with the cross. Bottom left, right.
Bottom left.
Bottom right.
Bottom right.
I don't see anything.
Oh.
Nothing is there. It's
Is it possible, Bhushit, that no?
okay, good. Cut it. 1 minute. Now I will. Now open the PDF. I'm sorry. Now I will. Now open the PDF. Oh, PDF. Now PDF. Presentation. Is it visible? Hello.
Not
Not,
yet.
No, sir.
not yet.
Share
Or
the
not
screen.
yet.
Sorry.
Please share the screen. Share.
Oh,
there
I
is a
should.
share option.
Okay.
Yeah, that's right.
I should share. Yeah. Okay. Okay. Share. Share. It says we can't display your shared content. Make sure that you are allowed permission to share content and then try again. Please give me permission to share the
Permission is already given.
saying. Share screen. We are unable to share this. What? It's saying that no, we can't display your shared content. Make sure that you are allowed permission to share content and then try again.
I think please leave the meeting and
Yeah,
rejoin.
maybe you
That is
leave the
better.
meeting and then rejoin. I think it will work.
And also send the PDF copy of the presentation.
Okay, that's what I think.
Please send that PDF file to me.
My email to.
Yes,
I will,
Navinder.
Sorry.
No, it's fine. Okay.
Oh, it's okay.
Navinder, I have emailed you the PDF.
Okay.
Has it come?
Not yet delivered.
Is it there?
No, not yet.
Then let me send it by WhatsApp.
Okay.
I will send it by WhatsApp. Navinder, I have also sent you the PDF by WhatsApp.
Okay. Yeah, I got on my Gmail also.
Okay. I'm extremely sorry for this mess.
No, it's okay. No problem. I'll just open it.
Just on the lighter side, I want to tell a story. Once I was listening to Nabal Are, he had more
Yeah.
difficulty than I was very happy. Also, another standard joke is, imagine if you have a quantum computer, how much uncertainties will be there.
So is it coming?
Yes, I am able to see, but it's not full screen for me.
Yeah.
Better. Okay, I think it's all in my code. I will have to make it bigger. Can you make it bigger?
Is it okay?
Yeah.
Now?
I see it.
Just
Okay.
change the
So,
slide.
yeah, so I will then change when you.
Yeah, it's
Anna,
coming. Good.
just
Okay, I
remind
think
me and then I will change.
screen complete. Are you able to see the screen well?
Yeah, we are able to see the screen well.
Okay. Then shall I start the talk?
Sure, sure.
Okay. So thank you, Navinder, for inviting me, and also thank you, Anil and Bharadwaj, director of PRL, and all friends for taking time to listen to me and bearing with me all these messes. So I'm extremely happy to be talking to you. I wish I would have come personally, meeting old friends like Prasanna and other friends. I was looking forward to meeting them. Anyway, it's good to have some virtual meeting anyway. So I'm going to talk about quantum origin or quantum roots of modern artificial intelligence. As you can see, I'm not going to talk about AI at all, but I will talk about how one led to the other in a very unexpected way, what we call as modern AI development. That's and the roots are in quantum. That's going to be my theme. So I will now maybe the next please. Yeah. So best wishes to young PRL. You are 75 years young. So congratulations to the visionary leaders, directors, past business, scientists, students, staff, and local for nurturing the great PR. It's a wonderful occasion to be talking to you. Next, please. Next. So, as you all know, please go on. There is, sorry, I think you jumped to the page. Please go to page 1. Yeah. I think something happened. So, we're in page 83. Please go to page 1. No, first page. But you're on page 81. Maybe there.
Yeah,
Ravinder,
yeah.
it's in the scrolling mode. It's in the scrolling mode. Make it
Yeah,
in
yeah.
the presentation mode.
Yeah, I could not.
Box.
I don't know what
Just
happened there.
run in that box.
Just a minute. So this one, and then
So now
I need to go to presentation, right? It is in the presentation
Yes.
mode. Okay, maybe I will just
No,
scroll
this is-
slowly
this
one
is-
by one. Okay, that is the. Okay, this is
Then-
the second slide,
Okay.
and this is the third slide.
Wonderful. So I said that both statistics and both science theory was born in 1924. This was the breakthrough in quantum light and quantum matter. Thanks to efforts of Einstein, quantum theory got a boost. 1925, wave mechanics, matrix mechanics were born. So we are celebrating, or UN is celebrating the 100th year of quantum science and technology. So really remarkable, happy occasion for all us quantum scientists. Next, please. Yeah, so briefly about my institute, the Institute of Mathematical Sciences. We have theory, research in theoretical physics, pure mathematics, and computer science. For young people, I may like to tell them that they may like to look at the website, and there are lots of visitors program, lots of programs going on. Please have a look at our website. Next, please. Then I spent my time, most of my time when I'm in India. Yeah, this is my institute. It's a green and beautiful place. And it's a small campus, but still green and lush green. And pandals and so on. Next, please. These are all the pictures that I took some years ago. So this is a neighboring campus, Indian Institute of Technology, where I also work now. It's a fascinating place. You see monkeys, you see deers, you see special deers and so on. There is a debate among students and faculty. Whenever you see a monkey, students say they are professors. Professors say they are monkeys. They are students. Anyway, that's a debate between students and faculty. Next, please. Then I spent nearly 4 months every year at Perimeter Institute. It's a great institute of theoretical physics. It's also set in a very natural environment. There's a green park and a little zoo and artificial lake. It's a wonderful place. I encourage people to look at the website. A very interesting program for young and senior. You can easily participate in it and visit. Next, please. Talking about Perimeter Institute, I cannot resist talking about Mike Lazaridis, who is the owner of BlackBerry company. He wanted to become apparently a quantum scientist, but poor guy only became a billionaire. So an opportunity came, gave $100 million to a young theoretical physicist, and asked him to set up a theory institute. That's how Perimeter Institute was born. It's a research institute with extensive visitors program. Past directors were Howard Patel, current director is Robert Myers, and another number is a lady, forget her name. So there are 25 distinguished visiting research chairs, more than a dozen named chairs. What is fascinating is an example of respect by a philanthropist for theoretical physics, open-ended research in science, something that helps transform society. It's very important to mention this open-ended research because these days, tendency of government and other money-giving agencies is to get some result day after tomorrow. In science, you cannot expect that. Things take their own time. And when it happens, it really is remarkable. And there are time scales. So apparently, at the beginning in India, when we started supporting science, we said that about 15% of the money are open-ended science. Many budget will be, you do not know what's going on now. So there are many other interesting examples like Nobel, Pauli, Uri Milner, Simons, Mahendralal Sarkar, and so on, Infosys, Krish Gopalakrishnan, who are supporting Shivanada open-ended science. So I wish there are more people like that to support open-ended science in India. Next, please. In this background, I got a news not long back. A lady gifted about $1 billion or few $1 billion to her alma mater, Einstein Medical College in Bronx in New York. And it means free tuition for everybody. So somebody was telling there are many billionaires in India. Let some of them follow this. Next, please. Anyway, this is a general thing. When we do science, what we do is we observe. Experiments are very, very important in science. Then we conceptualize the things and hypothesis and model building. And theoretical, analytical, numerical simulation method, machine learning, and so on help to be pushed further. Next, please. So, since we are in the quantum century, it's good to recall famous correspondence between Bose and Einstein, which is well known now. The rest is history. Einstein took Bose's notes very seriously and thought about indistinguishability very seriously and applied it to material particles. And then got Bose-Einstein condensation. Whole field has changed. Apparently, the work of Bose, indistinguishability notion and so on, helped Einstein to see through de Broglie's thesis, which he was correcting. And that's how de Broglie's theory got attention of Schrodinger, and then wave equation was formed. So Bose seemed to have played very important. Next, please. So science has performed miracles, the miracle of radio communication, miracle of material science, miracle of information technology, new possibilities. A new discovery in solar energy can put the world in the right path to eliminate climate change catastrophe. A new discovery in genetic engineering can make us angels. So quantum computers, room temperature, superconductivity, and so on. Next, please. So understanding some secrets of nature has transformed society. For example, the way we think, perceive our smallness, at the same time, unlimited potential. In fact, somebody told me that, science has made, we are a dot in the cosmos, tiny dot. We are maybe 1 meter or 2 meter long. We live for 100 years maybe. The universe lifetime is big, and space is big. So we are nothing but size. So it makes you humble. And then at the same time, it also tells you about the unlimited potential that we as human beings can do. So science has helped establishing fantastic social institutions and United Nations and so on. So we have, if you look at the development of science in the modern times, start with laws of Newton and Maxwell. The science was existing in as long as human beings, thinking human beings were there. But in a formalized way, it began from this time. So laws of Newton, Maxwell's equation, Darwin's theory, space-time relativity, quantum nature. Next, please. Now, since we are talking about quantum, if you look at the whole universe, in some sense, the universe is quantum. If you think about the theory of the Big Bang theory, people talk about quantum tunneling at the beginning of the universe. And then, inflation. Everywhere there is quantum mechanics, structure formation, matter formation. Similarly, if you look at the stars, what's going on inside, energy source of the Earth, for example, nuclear, fusion, so on. So everything is quantum mechanics. When you come to the Earth, there is atmosphere, there is stone, and mineral, magnets, chemical bonds, living systems, vision, ecosystem. So then you come to nanoscience, then you come to proton, neutrons, quantum gravity. So quantum is all pervading. Many of these developments have taken place in the last 100 years. It's amazing. Next, please. So if you look at the way quantum mechanics was developed, it's fascinating. It's one of the greatest creative acts of human mind. It involves guided by experiments, guesses, and intuitive leaps. For example, next please. Yeah, if you look at the brief history of quantum mechanics, it was Planck's bold hypothesis that photons carry energy quantum. And Einstein used it to explain bold way photoelectric. He didn't have a full theory, but he could explain what is going on within the limited assumptions and so on. Then came Niels Bohr. He said, I do not know what's going on. I see spectral lines. You can explain it if I assume existence of stationary orbits and transition between them. So that was the bold hypothesis. Then came S.N. Bose, who was very unhappy with existing derivation of Planck distribution by Einstein and others. Also, there was logical inconsistency. So he wanted to go beyond that. In the process, he discovered the notion, he introduced the notion of indistinguishability of elementary particles, namely photon. That opened the entire scenario of a new world. So that was S.N. Bose. Then came de Broglie. Again, de Broglie made a hypothesis that particles also have wave-like property. Like, we say that photon wave has particle property. Particles also have wave-like property. And Schrodinger formalized it using so-called wave mechanics. Then Heisenberg introduced matrix mechanics, Pauling went deeper, Dirac, and so on. The whole world is different now. So it's also a unique collective effort of human history, unique in human history, a forerunner to the modern collective character of modern science. And we cannot imagine science without any particular country. Everywhere we are so much collaboration. Science is in some sense it's a great unifier in the modern world. So the collective effort is unique in human history, which has happened in the last 100 years. Thanks partly to quantum mechanics. Next, please. Okay, this is about the Bohr's Planck distribution, light and lightness. So what did Planck, next please. So what did Planck do? So he wanted to explain this experimental observation of black body radiation. He could not explain it in one corner using classical theory. So he invented Planck distribution, a analytic form with a Planck's constant which carries his name. Next please. And then Einstein penetrated a little deeper and got bosons, cosines, condensation, and so on. Next, please. Yeah. Now, what is remarkable is the specific signature of Bohr's distribution, Planck distribution, is there at the distant sky. It's 3 degrees Kelvin in the black body radiation. This is in the microwave background radiation. That's supposed to come from the beginning of Big Bang. So nothing can be more support for quantum physics that has been ruling the game from the beginning. Yes, next please. So now many things have happened, bosons and fermions. So it was in the hands of Dirac and people like Fermi and Pauli that identical particles got separated into bosons and fermions. In fact, it was Dirac who named it as boson, the family of particles. Now we have got in the condensed matter new for statistics called abelian and non-abelian statistics. There are methods to do quantum computing, and also Higgs boson and boson. Quantum has just jumped into all scales from the level of atoms and electrons. We see superconductivity of helium-4, which is a macroscopic quantum phenomenon. Similarly, superconductivity at 200 Kelvin or 300 Kelvin is a macroscopic quantum phenomenon that you see quantum phenomena the table scale. Then there is matter wave interferometry and so on. Next, please. Okay, next. Next, yeah. I have an idea. So, what is the difference between Newton's laws and laws of quantum field? Deterministic sense. Classical mechanics and everything is very deterministic. And of course, the predictive power of calculus and so on are used. Next, please. So, laws are different at the atomic scale. That's where, I'm just giving some brief introduction. So, we have particle wave duality. What is happening is once you have this, make this hypothesis, many things profoundly follows. This the phenomenon of tunneling is very counterintuitive. Phenomenon of linear superposition and quantum entanglement. So just from few assumptions made by these great people, many things follow, which is captivating our attention and changing our world now, because they are getting used in many places, including in biology. Next, please. Sorry, I wanted to say, what I wanted to say was in the previous transparency, most quantum phenomena defy common sense. It's very counterintuitive. That's also an advantage because it's sharply guided by mathematics. So in classical mechanics, we have 6-7 dimensional phase space. Hilbert space is too big, so you have 6n dimensional, 3n dimensional Hilbert space. So it's in many problems, it's direct product of finite dimensional space. Like if you have includes 2 to the per dimensional space. Next, please. Now, what is very important is it's a quantum mechanics which gives stability to an atom. Otherwise, according to classical physics, you got a proton and an electron running around. Eventually, the electron will collapse and there will be catastrophe. Whereas, both stationary orbit holds them in place. So, in some sense, stability of atom is quantum mechanical. Then comes bonding. So, even though we got theory of elasticity, rigidity of solids, and various things before quantum mechanics, properties of solids, and so on. But the fact that atoms are held together is a quantum mechanical phenomenon. It could be chemical bond, it could be some other bond in which quantum physics deeply involved. Yes, next, please. Similarly, when you come to matter, quantum matter, photon is Einstein's the crystals, phonons. So many things are there. Notions like Fermi, bad insulator, topological insulator, holes, electrons, excitons, plasma, polar atoms. So next, please. Now, when you come to matter, what is fascinating is biological matter. You start with amino acids, water molecule, carbon dioxide, and so on. You combine them, you get proteins, nucleic acid, you get DNA. At the end is life. Amazing how over billions of years life has evolved from combination of atoms and molecules. That's where the emergence is happening in a fantastic way. Nature has found it. Yeah, next, please. This is just to give you one example of how quantum is playing such a fundamental role in biology. What I have shown is a picture of light harvesting complexes in which photon is absorbed, single photon, some of these pigments which are shown in this violet color, they create exciton, they hop around coherently, experiment it has been shown, and they go to the reaction center, initiates a chemical reaction. What's fascinating is, it was discovered about 15 years ago, that it seems to be happening warm wet temperature in an unexpected quantum phenomenon. If you don't expect a coherent propagation of exciton over long distances, like several few tens of nanometers, but it's happening. So now there are good justifications and theories for that. So even though biology, we talk about thermalization and so on, but at a deep level there is non-thermal behavior in biology. Even though a doctor may tell me that I am at 36 Kelvin or 36 Celsius. But at the molecular level, it's as if things are at zero temperature. Fascinating things are going. Again, biology has discovered quantum well before us. Next, please. Okay, next. I have already talked about it. Next. Next. Yeah, this is solar energy. Next. Yeah. So this, I just let me pause on it. How quantum changed the world now. It's very well known that we had vacuum tubes at some point. Then came semiconductor diodes, semiconductor transistor, field effect transistor, magnetic tunnel junctions, and so on. So the entire miniaturization started with a beautiful appreciation by Bodin, Shockley, and Grattan of application of quantum ideas in solid state. Basically, what you say is you have a block electrons in a periodic potential, filled bands and your empty bands, band gaps, there are impurity states. Then you can introduce a notion of holes and electron. There is an excess electron, either it's an electron, if you remove it's a hole. So it's as if Dirac's theory, which was discovered by Dirac, the relativistic considerations, is coming alive in non-relativistic context because of filled bands and empty bands. So what was positron, the Dirac's theory, becomes like a hole. It's a positive charge object in a semiconductor. So then came p-n junction. So the entire development of modern semiconductor physics started with a deep understanding of electron behavior in solids, notion of band gaps, notion of holes, electrons, mobility, and so on. This is very basically and beautifully fundamental. Now the world is very different. Next, please. So these are all the great pioneers: John Bodin, Shockley, and so what I'm not ending. So, and I also had the honor of meeting John Bodin twice. I was a postdoc at IAC. It was in 76. John Bodin was visiting us. So I had wonderful discussion with him about some charge density problem I was looking at. He was very receptive and made several interesting comments. And later at 87, I went to Arbanashan with him a colloquium on RVB theory of superconducting. John was again very receptive and had a wonderful time. So he is responsible for this quantum understanding of electronic behavior in solids, which has revolutionized our world now. Next, please. I just wanted to tell you how much this quantum things have changed us, our life. You know about Voyager 1 and 2, which was sent about 50 years ago. Next, please. The way it was sent was fantastic. I will not go into the detail. Now it's about beyond 10 billion miles. So light takes about few days to come so far. Next, please. But still, we are able to receive signal thanks to quantum sensitivity of the instrument, absorption of photons, and so on. So quantum has come in a big way in understanding even things beyond solar system. Next, please. Radio astronomy and so on. Yeah. Next. Okay. Now comes the main character of this, what I'm going to talk about. So, over in this theory, basically found out quantization of orbital angular. Then it was found out by Pauli that you need to introduce some intrinsic angular momentum if you want to explain things like Zeeman splitting. So he made a wild guess that the angular momentum of an electron just two values, either plus half h cross by 2 or minus h cross by 2. He made a wild guess and explained several things. Then in the process, he got what's called exclusion. Then independently, even before Pauli, apparently Bose thought about intrinsic angular momentum of photon. That's a very fascinating story about it. Apparently, Bose put that factor 2 to account for the two transverse polarization, which corresponds to spin projection in the transverse direction, the photon. In his paper, Einstein removed it, saying that you are saying something more important, so let's focus on the important thing. Let's not get diverted. So then it remained unfortunately unknown. Fortunately, Bose had told it to C.V. Raman in detail when he sent the paper. So C.V. Raman, when he discovered C.V. Raman and Bhagavan, when they discovered photon carry, the fact that experimentally they proved that photon carries angular momentum 1. They refer to the discovery by Bose, that paper. So it's a fascinating story. we and Robert May wrote an article on boson bloom. It's available in the website. You can easily download it freely. I have told stories about it. It's a fantastic story. How Bose also had intuitively made a guess that photon, if you think of it as a particle, identical particle, carries an intrinsic angular momentum. Same way, Pauli thought about intrinsic angular momentum. Now there is no stopping. Electron has a spin, proton has a spin, neutron has a spin, nucleons, neutrino, quark, everybody. Similarly, condensed matter excitations like magnon, phonons. Similarly, we go deep into quarks and so on, gluon and theory, they all carry spin. So what is remarkable is fundamental role of Pauli exclusion interaction leads to very special interaction which are called exchange interaction. This is what I want to say. Suppose you think about classical magnets. When you have two magnets at a distance, there is a dipolar interaction. Let's see. But when you bring two electrons close by, because they are identical particles, because they obey Pauli principle, because they carry spin, very fascinating things emerge, something called Heisenberg exchange, which Heisenberg wrote down as some spin dots S1 dot S2 times J. This was the famous work of Heisenberg exchange. He didn't go deep into the origin of it. He said it's a distinct possibility that comes from exclusion principle and identical particle character. Then Mr. Kuhn came. He not only explained some spectroscopic regularities. He said that there is a Hund coupling which puts spins parallel when you have unfilled D shell or F shells and so on. Then people like P.W. Anderson, Kramers, and sharpened it. Said not the notion of the solid state direct exchange and super exchange and so on, which gave you ferromagnetic or antiferromagnetic coupling, which is written typically in the form of two vector product S1 dot S2. So this is never possible in classical mechanics because it's always a dipolar interaction. So that's where the spin enters in very beautiful way. And also, if you think a little more deeply, Fermi sees something very important in copper or in iron. They are it's a Fermi sea which eventually leads to magnetism in a fundamental way. So I will explain these things in some detail later. Something called XD exchange interaction or KQ interactions. Next, please. Yeah. Now, for example, let me take a hydrogen molecule. Apply the theory of Heisenberg. Basically, what you see, you put two electrons, a spin singlet state. So that means orbital part is symmetric and spin singlet part is antisymmetric. That's an exchange coupling. It's coming from some antiferromagnetic coupling between two electrons. And then that's what it is. And then this already brings in the beautiful idea of quantum entanglement, which is ruling the day now. That means two electrons, they are exchange coupled. If their state is up, down, minus, down, up, then in principle you can separate the two hydrogen atoms, the molecule, adiabatically slowly, and there will be so-called entanglement. Since we make a measurement of up spin in one electron, one end, you can definitely say the other electron is down and so on. So there is a non-classical correlation that emerges. Simple idea of exchange interaction between two electrons. It's the beginning of. It's also at the qubits levels and so on. Next, please. Now, this I just wanted to bring this famous poem of William Blake. He said, "To see a world in a grain of sand, and heaven in a wheel flower, hold infinity in the palm of your hand, the eternity now." For example, I told you about the example of hydrogen molecule. Already, a simple example tells you what's going on. The level of this molecule, this quantum entanglement comes everywhere. For example, the physics of black hole. People talk about quantum entanglement between, the so-called information paradox are explained using quantum entanglement. So suddenly, what you learn from a simple grain of sand suddenly becomes applicable everywhere. And this is well known in condensed matter physics. For example, people studied superconductivity. It was Anderson who said that the plasma emergence in a neutral superconductor in their charge is like a mass gap in elementary particle. So that became famous. Anderson Higgs boson. So the Higgs mechanism, which is valid at a very scale of electron mass and proton mass, neutron mass, and so on, they became from solid state physics. So you can. That's a great thing about science. many phenomena that happens at some scale gets reflected elsewhere. So there's a big network of web of science. That's something fascinating. So whenever you are doing something, don't think it's just applicable there alone. One day you may find it applicable elsewhere. Next, please. So now let me tell you about how am I doing with respect to time? I started at 4, so
Yeah,
I
we
have to
started late, so maybe half an hour over.
finish it, yeah. Okay. So since I'm talking about quantum roots of AI, so look at who would have thought ferromagnetism or antiferromagnetism will lead to AI eventually. Metallic iron is a ferromagnet, and so is GMIN bar. Metallic chromium is antiferromagnetic, so is insulating. So we understand many of these things. Then there was people who were fascinated by the fact that if you take copper, put iron or manganese in copper, you find a very peculiar behavior, cooperative behavior. Next, please. In fact, this was the experimental observation that you saw very funny susceptibility behavior when you have a dilute concentration of manganese in copper. So this was called spin glass. Nobody understood what was going on because it's a very random thing and how any cooperative phenomena can take place. Next, please. And then there it was very important to realize, suppose I take a copper lattice and randomly put some manganese ion. Then I look at how the two manganese atoms are coupled. Of course, there's no direct coupling, they're well separated. However, there are conduction electrons running around everywhere, they're in block states. So they mediate so-called Guderman-Little Casio interaction. Now, we do not want to go into the time to go into the quantum mechanics. You will find that in a very simple perturbation theory, you find the exchange coupling between two electrons as a function of distance is oscillatory in character. So if at some separation they are ferromagnetic, at some separation they are anti. So you have a random collection of spins. You will find if you take any pair, some of them would like to be parallel, some of them would like to be anti-parallel. Next, please. That's where the beautiful notion of frustration came. That's where our heroes, Sam Edwards and Anderson, came. So they were worried about this problem. And they came up with some model. This is Phil Anderson. I took this photograph in 1921 at great man. And he is one of the greatest physicists of our time. Next, please. I was also telling you about this grain of sand and so on. Look at the carrier of Anderson. Started looking at dirty things like NMR line shape, quantum antiferromagnet, double exchange, and so on. So there are tower of Anderson's models. Wherever I have put double star, there are Nobel Prizes that have been eventually given based on that, not for example, if you take spin glass, Giorgio Parisi got Nobel Prize. Recently, John Hopkins got Nobel Prize. Because the origin of that's what I'm going to explain now. So his insight into dirty things and simple rust and so on, what insulated and so on, had profound consequence. That was Phil Anderson. Next, please. So it was not just by Anderson and many others like Manier that suppose I have 4 spins which are on a simple square. Then if they are ferromagnetic coupling, they are a happy order. All spins can be up or down. But if it's antiferromagnetic, if you have a square, there is half the spins can be up, half the spins can be down. Every bond will be happy. But suppose you have 3 spins which form a triangle, you will find there is a conflict or a frustration. If 2 spins are antiparallel, the other fellow goes to be parallel. So that means there is enormous degeneracy. So the spins do not know how to order. So there is a fight. Imagine this fight happening any number of times. Next, please. That's where, Sherrington and Kirkpatrick simplified Anderson's model that we'll complete later. Next, please. Yeah, next, please. Next. Yeah. So the important point is what Anderson and Edwards did was, okay, I have a collection of spins which are interacting. As if you pick up any pair of them, it's like a random couple. It's with some probability it will be ferromagnetic, some probability it will be antiferromagnetic. So let me think about a random model in which couplings are distributed uniformly in a ferromagnetic and antiferromagnetic way, and do some average study. Then they found out fascinating results, and they could not solve the problem. They solved it and approximately gave some insight. Then Sherrington Kirkpatrick made it even simpler, gave some insight and stopped it. Then I will come to such Devi a little later. Next, please. Then came Giorgio Parisi. What he did was he took the Sherrington Kirkpatrick model and he solved it exactly in beautiful mathematical field. What he found was, if you take a simple ferromagnet and antiferromagnet, look at the energy landscape, there will be two minimum. All spins up or all spin down if you have an icing spin. Or a minimum in which you can continuously rotate. So the phase space will be very simple. The space of ordered state will be very simple. Whereas if you take a spin glass, it's a very rugged landscape, and also Parisi found out this hierarchical organization. That's why you got Nobel Prize. Famous Parisi's ultrametric structure. Next, please. Okay. Then there are beautiful mathematics. I am now going to next, please. Now, how it is? Then there is a mathematics behind Parisi's work. Next, please. Yeah. What was fascinating was this study of spin glass immediately woke up people and they started thinking about how brain works, how immune system protein folding, wherever there is complexity, wherever there is competition, wherever there is frustration, there are beautiful mathematics which are similar. So that's where the science of complexity spin glasses came. So many notions came. Next, please. This is where our hero comes. John Hopfield was a close collaborator and close friend of Phil Anderson. He was also young faculty at Princeton, and where Anderson was also there. John is well known for his work on polariton. He introduced the name polariton. He was a student of Al Overhauser, a famous condensed matter theorist. Then John started thinking about biology problems. He started working on electron transfer in biochemical reactions. At some point, he was fascinated by brain. Then the story is, he was very familiar with Anderson's model of spin glass, where upspin, downspin frustrations, and many bonds on the landscape, complex landscape. So he basically used that idea in a very beautiful way. He said that I want to simplify a collection of neurons, the simplest mathematical form. So there is a neuron which is connected to another neuron, connected by something called axon. What axon? What the neuron does, when it fires, it allows the other fellow to fire or stop firing. So you can crudely say a neuron is in two states, either firing or not firing. So that's like a spin up or down. So now if you think about the mathematics of it, it becomes very simple. It becomes like a spin glass model. But then the Jij, what it is, that's a question. So what John Hopfield did in a characteristic solid state physics was he simplified it and he allowed it some dynamics of this, and he found out beautiful what is called associative memory model. Next, please. Yeah, the thing is about. Suppose I have a potential minima like this configuration space. Then there are minima. So if you put the particle in the, let's say, top position, slide down to the minimum. So imagine the brain. Since I said that brain neurons are like spins. So suppose I remember something. There's a particular pattern of firing. That one neuron is firing, another is not firing, and so on. So then if that pattern can be stored in some way, then if I take it very close to that pattern, slide down to that. So we use the idea of spin glass dynamics to show that there will be memory that can be associated with connections in the brain. This is where the fascinating thing happened. I have no time to go into the details of some Hep's rule and so on. So what he did was he wrote down an energy function where there is no energy involved, but it was an imaginary energy function. Then some Wij connection between spins, which is connected to something called Hep's rule. And then he got beautiful results, showing the whole artificial intelligence. Next, please. Okay. Now I will not again. Sorry, I have no time to go into the details. There was Terry Sanos. He was a student of John Hopfield. He was a student of general relativity at Princeton. He was inspired by John's work, and he started working on John's neural network idea. Then wrote the beautiful paper, he and Hinton, what's called Boltzmann machine. The idea is the following. Let me very crude. That's at the heart of many of the modern machine learning. what you do is you have some input, you want some input. So at the beginning, once you give an input and if you start with some random connection, you will get some random output, nothing to do with input. But then you anticipate some output. Right? Suppose I say that 2 plus 2 should become 4, it should not be 7. So I anticipate that out, then I change my circuit so that I give several set of inputs, the right output. Still, I get the right output, so I change the circuit. This is called training this. That's what Boltzmann machine does. They use some Boltzmann weight and so on. And wonderful thing was it started working. In fact, in '96, Terry Sanuski gave a colloquium at Princeton. What he demonstrated was he had a machine in which the machine reads the English text. And if there is a grammatical error, it says there is an error. And it tells you what's the error. Then how did he achieve it? What he said was he had an input channel, then output, random connections. Then he, of course, at the beginning when you give some, you get some nonsensical result. Then you change the connections till you get the right. That's called training the machine. So his machine became 95% accurate. It was fascinating. So at that time I asked Terry, can you get the grammar book out of that circuit? He laughed. He said, "That's $1 billion question. We'll come to it a little later." So that's how this training notion and how do our brain get trained. That's where the Hep's rule and so on. So whenever we experience something, certain connections between neurons are formed, excitatory or inhibitory connection. So that's connected to Hep's rule. So then reinforces slowly we start learning. So as a child, there is a theory that we start with some random connection. As we grow, they get pruned and we start learning things. So that's exactly you do with machine learning. Next, please. Now, there are fantastic development. I encourage young people to look at some of these papers. David Hinton, who got Nobel Prize with John Hopkins, he what's called deep learning algorithm. There are simple algorithms. If you go deeper, you get many things. There is something a large language models. It's a fascinating paper. The title is "Attention is All You Need." The idea is that as the machine is learning, it's not blind. It's learning how it is learning. So you pay attention to what you have learned, then you do it faster. That's called attention is all you need. That's a Google company, group of 10 people. That's what last started large language model and ChatGPT. Then a young friend of mine from UCSD, Yu Zhuang, he asked the question, can machine discover quantum mechanics? We talk about machine solving various problems. Can it discover quantum mechanics? He wrote a beautiful paper called Introspective Machine. He said that by proper management, you can even get a machine discover quantum mechanics in limited way. And then he keeps saying that let's use not the standard mathematics of category theory to understand this. So let me stop here by saying that you see, you started with quantum physics, idea of elementary quanta of energy, then idea of identical particles, the idea of quantized angular momentum, the idea of intrinsic spin, quantized spin of angular momentum. Then you come to Fermi sea. Then you see magnets, ferromagnets, antiferromagnets, spin glasses, and so on. Then you try to theorize them in simple model. Then you find profound consequences. Nobody would have expected that spin glass would have given an idea for operating instant brain. And we have gone much beyond that. And we don't understand brain, but at the same time, we have created artificial intelligence, big mess, which is shaking the world now because it can be made good use of and also bad use of. We have to be careful. So, for example, AI, somebody connected it with a very super efficient secretary, but she can be erratic 20% of the time. So be careful. So if you take AI and use it carelessly, you can go wrong. But if you use judiciously, you can go a long way. Because it can be great AI. So that's what the message is, that nothing in science, when Pauli discovered Pauli exclusion principle, or Bose introduced the notion of spin, or Pauli introduced the notion of spin half and so on. Nobody would have thought it would have such a profound consequence. About 1 century has led to so many things. Like another thing is, for example, take nuclear spins, nuclear magnetic resonance. Who would have thought it will help in imaging? And in fact, the entire field of medicine is dominated by NMR imaging, similarly positive tomography, and various things. So quantum physics has gone in a big way. I'm not talking modern electronics and stuff. I'm just talking about very simple things like now these artificial intelligence has come. And AI is changing the world in the sense it can very helpful. Like it's apparently helping field of medicine enormously when you have big data and analysis and also various fields. So let's use our quantum physics and so on in a wise way, and let's make the world better. Thank you very much. I'll close here. I think I completed 50 minutes or so. So I'll be happy to answer some questions. Naveen?
Yeah, Partho, Namit,
Sorry?
you have to, my colleague Partho Konar is going to handle this question answer session. Partho, you have to unmute yourself.
Yes,
Okay,
I am.
Hello. Ah.
Yes, yes, I am audible.
Yes, yes.
Okay. So thanks, Professor Baskaran, to give a
Yeah.
extremely insightful demonstration of different quantum phenomena, and also you talked about very early phase of the machine learning, how it was evolved from the basic structure of spin glass and energy landscape and quantum phenomena, and
Yeah.
actually idea of memory evolved from that, and that was the very beginning of this machine learning phenomena and
Yeah,
the very earliest development. So let us open up for many questions from the participants who are already in this group, or any questions I get in the chat box. So I'll read that one.
Okay.
So any of these participants can raise
Yeah.
their
Can you ask her? Partho, can I ask one question?
Yes, go ahead.
Yeah, thank you, Professor Baskaran. It was a wonderful talk. You in the last slide you have written that artificial intelligence can discover quantum mechanics.
Yeah.
So, yeah, but can it discover quantum gravity?
Yeah, exactly. That's a good question. So, or can
Yeah.
you discover dark matter? What is dark matter?
Yeah,
So there are
dark
many
matter.
problems. Exactly. So apparently, with proper insights and proper use, proper guidance, you can go a long way. I do not know how long, but it's a big question because this, when I say can it discover quantum mechanics in a very limited sense, what Zhuang does is he gives some set of data which corresponds to wave functions. They ask the question where it comes from. So one of the possibilities is a Schrodinger-like equation with the right constant. So he says, then it's not a standard machine because this machine thinks about how it has done it on the way, like large language models. Now you says that you have to use what is called category theory, very deep mathematical, apparently very generalized mathematical theory, which can be used. And so lots of new possibilities are there. One should be careful, of course, but one can. I'll be wonderful. I'll be very happy if quantum gravity problem gets solved by machines one day. But we should be not see. This is where the hype comes. Many of these media and so on, they make a lot of hype and many raise questions like what is consciousness? Does machine have consciousness and so on? Will the machine kill us eventually? And so I do not know. So these are all questions which I have no answer, but I can, as a solid state physicist, find out the beautiful use of quantum in some sense to the modern development. But with the wise and judicious use of this, we can go a long way.
Yeah, thank you.
Can it? Okay. I think Prasanna wants to have a question. Please go ahead, Prasanna. Unmute yourself.
Unmute yourself, Professor Prasanna. You have to unmute yourself.
Is it okay
Yes.
now?
Yes.
So Bhaskaran, it was a nice talk. I'm just curious to know, going through these lines, can one see whether artificial intelligence can develop consciousness?
Sorry, will you please repeat, Prasanna, louder?
Whether artificial intelligence, can it develop consciousness?
Yeah, exactly. That's very important. So the question is, what is consciousness? In fact, this question was asked by Crick some years ago. He said, there's a lot of debates even among philosophers and neuroscientists. What is the consciousness? Can it be sharply defined? Apparently no. But then the feeling is you and me understand what is the meaning of being conscious, roughly. So what Crick says is, let us make some hypothesis and test it. He makes a beautiful statement. We have these machines now, fMRI, functional magnetic resonance imaging, and so on, which tells you from the pattern of brain firing, you can see whether somebody is happy or unhappy, grammatically correct or wrong. So now, given that correlations between neural correlates and conscious state, then we make some progress. He says they have made some progress with visual consciousness, but still far away from anything. In fact, since you asked this question, John Hopfield is a person whom I knew very well, Princeton, in '84 and so on. So he gave a talk at Math Science Online. He got Boltzmann Award. He and Deepak got Boltzmann. He will be honored them. So I was talking to John and I asked him, John, what's your impression about the question of consciousness? Do you understand it? He said that Baskaran, he put his hand down on the floor. He said, Baskaran, we are here. That question is up there. So there are many kind of, some people are very confident that machines have consciousness, but then it becomes very philosophical and a tricky issue. I do not know. That's my long answer.
Yeah, Partha, I have a question.
Yes, go ahead, Vijay.
Yeah, Professor Bhaskaran, nice talk. I just wanted to know, say, you talked about only the general principle of artificial intelligence, and you related that to quantum mechanics. But the generally, artificial intelligence that what people are using, that is based on classical mechanics. There is also something called quantum artificial intelligence.
Exactly.
So that the general principle of artificial intelligence, whether that is really quantum origin, or one can also relate that with the statistical physics based on classical mechanics.
So since it's a general colloquium, I was very superficial. Not this, for example, in the neural network model, there is no quantum mechanics. You have a big neuron is firing or not, that's called an icing. It's not nothing of quantum mechanics. But then when you go deep into it, for example, people like Roger Penrose, he says microtubules, they support some cavity modes. They are acting like qubits. And some people say neutron spin can act like a qubit because they have lost long. So that's a new game altogether. Quantumness in neuroscience and so on. And also in the development of machine learning, they use some of the ideas of tensor networks that comes from many-body theory that also has got mixed up. So I'm not talking about that at all. I'm just talking about what a computer science will do. So like a contribution to computer science. But that's why, there is more fascinating possibilities here. And what you are pointing out, they are yet to come. It's a great time for young people to jump into it.
Yeah, thank you. Thank you.
Any more question? Okay. So I have some question and comment. So let me ask you. So one thing is related. Sorry, I get echo. Once the thing is the question related to it, Prasanna, what I realized that many of these phenomena, what was earlier thought as a completely impossible for a machine, now become a possibility nowadays. As for example, abstract is one possibility. People maybe last 5 years back, people thought abstract art can be done by a machine. I have a related question. When you are talking about this in your last slide, when you are talking about this machine learning development for the quantum mechanics. So my question is that normally machine learning methods learns from the data or learns from the example. So once it did not have the setup or mathematical structure of the quantum mechanics ready, whether it could develop that quantum mechanical mathematical structure, that time it was not available. So that new mathematical structure, it can evolve in that way.
Exactly. So that's very important. For example, if you look at the way human beings discovered quantum mechanics, Planck made a hypothesis by looking at spectral line. Then Einstein worried about photoelectric effect, and Niels Bohr talked about spectral lines. So can machine replace these? I do not know, because it can really. I think we are at the brink of some important development, and even classical mechanics. Can you discover structure of classical mechanics given enough data? Can you discover the 3 laws of Newton? So these are all questions that have not been asked seriously, because people are excited about the applications at the moment. But it's worth thinking about how far the machines can go. And also another important thing is the power of modern science and physics, particularly, is an analytical component of mathematics. Like, look at Maxwell's equation. Maxwell discovered, because of used calculus, and they made it beautiful, and electromagnetic waves were born, and Maxwell's equations were there. They were born. Whereas with machines, there is something very different. So I find this analytical component missing. Power of human mind to create analytical mathematics is missing in machines. I think that to that extent it seems to be limited in my view. I do not know. Because, for example, we do special functions. So many beautiful things are there. Complex functions, theory, mathematical structures, very profound structures are there. If one day machines can conceive them, then I'll have more respect for machines. I do not know. I think we're at the beginning of a big game.
Yeah,
That's my answer. I'm not an expert in, but I'm enjoying it from a distance.
Yeah. So I remember that recently I was looking at one paper. It looked at the different observational astronomical data, basically position of the different planets and moons, those data, and it analyzed through machine learning, and it come back with this law of gravitation, basically from the first principle. Only this observational data gives you the feedback, and law of gravitation you can come back. So it was a kind of big step. It was talked about that from the very first principle you can come through the machine learning. So yeah, so this is a small step, but in quantum mechanics, as you have to evolve, you have to develop different mathematical structure, and you have to. So that's why my query in that direction.
So I really do not know. It's a fascinating field. Lots of things are happening.
Yeah.
And so happens I listened to the talk by this ED from Stanford. Because I was thinking about it. I spent 6 months trying to see if quantum mechanics can be discovered by machines 5-6 years ago. And I gave up. And this young man gave an answer. I was very happy to listen to it. But I think, as they say, one should be extremely careful, because it's a new power that we have got. We should use it very, very properly. Like, for example, the notion of hallucination. I remember somebody showed me, they asked ChatGPT to write an article, use a reference which is totally imaginary. Combination of authors, everything, it can hallucinate also. So one should be extremely careful, particularly when it is coming to. That's where, I think some moment of training of telling young people not to overuse it. It's important. It can be a good guide. Like a sports car, the sports car, you can go to somebody, you can't fly immediately, even though you may jump occasionally.
More question?
Sorry, I don't think I gave a very coherent talk, but that's the way, it was my. Sorry if it was too incoherent.
Yeah, it was okay.
Anybody can raise their hand.
Actually, this was a very good talk. But generally, when it comes to quantum mechanism and many theory kind of things, so that is little tricky. You know that. Yes.
Okay, I don't see any more hand.
So if there are no questions, then we conclude the session with a vote of thanks. Yeah, now I request colleague Dr. Bhusit Prasno to present vote of thanks.
Yes. So this is the 105th episode and 105th vote of thanks so far. So I would like to thank. I think there is some echo. Hello.
Please, everyone unmute. Bhusit, can you start again?
Yeah.
I think everybody should mute except the speaker.
Yes. So this is the 105th episode of PRL ka Amrut Vyakhyaan, and I am presenting the 105th vote of thanks of this episode. So first of all, I would like to thank Professor Baskaran to be with us and delivering such an interesting lecture and very insightful information on the topic he presented today. I would like to thank all our attendees on WebEx as well as YouTube for joining us for this lecture. We thank our director, Professor Anil Bharadwaj, and our dean for constantly encouraging our committee for continuing this show going on. And we are getting, very good speakers week after week and month after month as a result of that. I would like to thank each and every member of the Amrut Vyakhyaan committee for their support at various capacities. And with this, we conclude today's episode, and we will, see you again in next episode. That is 106th Vyakhyaan in next month. Thank you. Have a nice time and good night. Thank you.
Thank you. All the best.
Yeah, thank you, Professor Baskaran. Thank you very much.